Hello, everyone. Today's talk is The Proton Aurora by Eric Donovan. Eric is a professor of physics and astronomy at the University of Calgary. He did his PhD in physics at the University of Alberta, where his thesis was on magnetic mapping. He has since focused mostly on the use of auroral observations to remote sense magnetospheric dynamics and explore the physics of the aurora. He co-leads the Themis ASI program and is PI of the new T-Rex auroral observing system in Canada. With that, Eric, you can take it away.
Okay, thanks Kyle for the introduction, and thanks to you and Dave and Homayan for letting me give this talk. I mean, it's actually really it's because of the absence of face-to-face meetings these days. I think you guys have done a huge service for our community, and so as you said, I'm talking about the Proton Aurora here today, and I'm not going to give you an overview of what I'm going to talk about. I'm actually going to work sort of backwards, sort of starting with some history right back to the beginning of proton auroral observations, and then walking my way backwards to how we use observations of the proton aurora to remote sense some things that are going on in the magnetosphere. And I think it's a really valuable thing for us to observe, and that we've learned a lot about the magnetosphere and magnetospheric physics as a consequence of studying the proton aurora. And so I'll just leave it at that. So I start out with, as I say, some history. And I'm just going to say that, you know, most people, and I'll get to the brightness of the proton aurora in a little bit, but most people, when they talk about aurora, what they're talking about, of course, is aurora caused by excitation of upper atmospheric atoms, molecules, and ions by precipitating electrons from the magnetosphere. And the colors that we see in the aurora come from, you know, the specific emissions that are, you know, prevalent in the auroral spectrum. And, you know, I mean, a lot is understood. I mean, the electron aurora is a partially well understood phenomenon, and we've made a lot of progress on it. And the proton aurora, I would argue, is actually a lot better understood than the electron aurora, because it's a lot simpler mechanism, and because it's a much simpler mechanism, it's a lot easier to tie it directly to things that are going on in the magnetosphere than it is with the electron aurora. Now, the observations of proton aurora date back to, you know, people who, if you know a lot about the history of auroral observations, you'll know that Scandinavian, and in particular Norwegian, physicists in the late 19th century and up to the mid 20th century did a lot of very good work on auroral spectroscopy. And in 1939, a guy named Vigard did some observations with spectroscopic observations of the aurora, and he identified an emission line in the aurora that was the Balmer beta line in hydrogen. And in fact, you know, I'm showing here that the bottom plot here is the Balmer beta line from, it's sort of the bottom plot here is the Balmer beta line from observations in a lab. And this is the auroral spectrum here showing this Balmer beta line, but what you'll notice is that it hasn't got the same shape as the laboratory line, and that's because there are two things that are going on here, both of which have to do with Doppler, the Doppler shift. One is the emission line is significantly Doppler broadened, and the other one is its mean, or the bulk of the line is shifted towards the blue end of the spectrum, which corresponds to, of course, particles which on average are coming at you when they emit the photons. And so this was the first identification, really clear identification of the proton emissions in auroral spectra, and this has come to be known as proton aurora. I'm just going to go through some basic things that have to do with the proton aurora that were understood in the first few decades that people were looking at this phenomenon. So first of all, what's happening, and this is a little bit cyclic because it's actually hard to draw a straight line through the literature, and so it's kind of starting with something that happened a bit later. But the understanding is that, of course, the Balmer beta line is an emission in neutral hydrogen. And what is happening, it turns out, is that protons from the magnetosphere are spiraling down the magnetic field line and then getting into the increasingly dense upper atmosphere. And as they collide with atmospheric constituents, they undergo what are called charge exchange collisions. And that means that this positively charged proton picks up an electron, leaving a negatively charged or double negatively charged ion, and it picks up that electron and becomes neutral hydrogen. And once it's neutral hydrogen, it's no longer spiraling around the Earth's magnetic field, and it just travels in a straight line until it hits something else. And then when it hits something else, it will probably lose that electron in that collision. And then it continues spiraling down the magnetic field line, and then it hits something else, and then continues off on a straight line. And then as you get to the denser and denser atmosphere, you start to get these weird trajectories, which are like almost like a cycloid, but that corresponds to 3 or 4 collisions maybe per gyro period, and 3 or 4 charge exchange collisions. And so the trajectory is a very odd trajectory compared to incoming electrons in Electron Aurora. The other thing is that all of the emissions that comprise the Proton Aurora happen while the proton has an electron with it, while it's the nucleus of a hydrogen atom. And on top of that, so I'll just leave it at that and go on to the next slide. Okay, so this business of the Doppler broadening, I couldn't find as good a figure of this for the hydrogen Balmer beta. The hydrogen Balmer alpha is also present in the auroral spectrum, but it happens to overlap with a bunch of other emissions and is rather difficult to look at. And Lyman alpha is a prevalent emission as well, but it's absorbed by the atmosphere, and so it can be observed readily from space, but not from the ground. And so we tend to use Balmer beta when we study Proton Aurora from the ground, because it's the emission that is most easily teased out of the larger auroral spectrum. So what we're seeing here is the idea of a and this now we're talking about, imagine that the proton is spiraling down the magnetic field line, and then it undergoes a charge exchange collision. And when it does, it just starts to move off in whatever direction it was moving at the time, okay? And so then when it emits, if you're looking at the emitted photon from the ground, then, or from a detector, then what you'll see is that photon will be Doppler shifted in one direction or another. And so if you're looking transverse or across the trajectory, the guiding center trajectory, if you will, then what you see are pretty much as many photons moving away from you as moving towards you. And what that does is Doppler broadens. In this case, this is the Balmer alpha spectrum, but it Doppler broadens that spectrum. And then if you're looking up the magnetic field line at the incoming particle, then at the incoming hydrogen/proton trajectory, then while the component of the motion along the magnetic field line is towards you. And then what you have then is this Doppler shift, which is largely blueward. There's a little bit of red shift, but it's largely blueward. And this happens, it's the same thing in the Balmer beta, same thing in the Balmer, in the Lyman alpha, but again, we tend to focus on Balmer beta in all of our proton auroral observations from the ground, or most of them anyway. And so and in fact, this blueward shifting of the hydrogen emission lines, this was identified by Vigard in 1939, and as the first solid evidence that auroral emissions were being caused by particles that were raining down on the upper atmosphere from above, from further out in space. And so the Proton Aurora, oddly though it's the least known of the aurora, is also the aurora that gave us our first, as I say, incontrovertible might be a strong word, but proof-ish that the particles in the aurora were coming down from above on the Earth's upper atmosphere. Now, a guy who lives in Montana, not too far south of here now, wrote a paper in 1975. His name is Jerry Davidson. And in this paper, he demonstrated, or he sort of explored the consequences of this kind of pachinko-like path that a proton will follow as it becomes hydrogen proton, and so on, as it colliding up to 100 or more times with atmospheric constituents as it comes to rest. And then what he explored was how, if you had like a beam or a sheet, an infinitesimally thin sheet of incoming protons, then this process of charge exchange collisions and then brief times periods where the proton moves in a straight line trajectory. And what that does is it would take an input signal that is a infinitesimally thin sheet and then broadens that out. And this is largely responsible for the very structureless appearance of the proton aurora when you image it or when you measure it with other devices. And so because if you have a kind of a structured input, everything gets spread out 50 kilometers or 100 kilometers or 150 kilometers, depending on the kinetic energy. And this spreading tends to be maximum in the tens of keV range. It gets smaller as you get to higher energy for one reason, and smaller when you get to lower energy for another reason. So you get this broadening in the range of energies that it turns out most of the protons that are causing this fall into, because those are inner CPS energies, it turns out. Now, so what does this look like? So we have, back in 2001, our research group was running a camera in Gillam, Manitoba it was a filter wheel camera, and it had a number of different filters, mostly for electron auroral observations, but we had a 486.1 nanometer, which corresponds to the Balmer beta line, the H, we just call it the H beta aurora. And so we could image the proton aurora when it was relatively bright, because this is I'll get to this, a very dim emission. And then there's a discrete arc here seen not simultaneously, but within seconds, with the oxygen green line filter that we had in that camera at the time. And so if you look at this, this is sort of typical for what you would expect of the proton aurora. It's a relatively thick in latitude. In this case, this would be probably 200 or 300 kilometers in north-south extent. And it really has a fairly sharp cutoff at the poleward end, and is relatively, if not totally, structureless within it. I mean, there's a peak, and there might be some gradation along the proton auroral region, but it's not structured in any way like pulsating aurora, patchy pulsating aurora, or discrete arcs, or polar cap arcs, and so on. In this case, this shows something that I'm going to come back to in the last slide of this talk, which is that arcs, and I'm just going to say this right now, but auroral arcs, it's kind of conjecture, but it has been said once in the literature in an old paper of Larry Lyons back in the 80s, and he can't remember why he said it. It's one line, but the auroral arcs, in my experience, occur either always poleward of the peak in the proton auroral brightness. And this is just something that I've looked at so much of this data over the years, and that seems to be a rule that holds fast and true. And what Larry had said way back when was that always occur in a region where they are surrounded by a full ion loss cone. And I'll come back to that statement if I have time as we move on. Okay, so I'm just going to show you kind of different ways that we have of looking at this, and just go through some basics about what's going on here. So first of all, what we've got is back in early part of the 2000s, this is what the optical scene looked like in Canada for doing these kind of observations. We had 4 cameras and 4 Meridian scanning photometers. And Meridian scanning photometers were really cool. People from anybody who was working in our field in the 90s, I think, in the magnetospheric community would be familiar with the Canopus Meridian scanning photometers, because they were used in a whole bunch of really important magnetospheric studies. The data from them were used in a bunch of important studies, and I'm going to mention some of those at the end of this talk. And these meridian scanning photometers, what they do is they just have a photomultiplier tube, and they have a filter wheel which is spinning very fast. And from the point of view of the proton auroral observations, well, they had eight filters, and 3 of those filters did a nitrogen line, oxygen green line, oxygen red line, and 2 of those filters did the H beta, and then 2 of the filters were provided background estimates for looking off of auroral emission lines. And the reason why we had 2 filters doing the H beta was because turns out the signal is so weak that we had to co-add photons that were coming through the 2 filter slots, or there wasn't enough signal to get good Keograms and good meridian scans. And so what this does is this scan from north to south, south to north, and that would take 1 minute. And we had either a 30-second or a 1-minute data product, depending upon who you were getting the data from. And what it gave you was intensity as a function of elevation angle in 4 scientifically interesting wavelengths: the 3 electron aurora wavelengths and the 1 proton aurora wavelength. And then this here is the left-hand panel is showing you a stack plot of Keograms. I'm just presume people know what a Keogram is, and from Rankin Inlet, from Gillam, Manitoba, and from Pinawa. And what you're seeing here is the diurnal variation of a quiet day proton aurora. And it turns out that what we're really doing is staring into the distribution function, the integrated distribution function in the inner part of the central plasma sheet. But this is showing you this is a typical behavior that you see night after night after night after night with the proton aurora. But it comes in from poleward of you and then moves down equatorward, getting to its, if there's nothing dynamic going on, getting to its lowest latitude at about 2330 MLT on average, and then retreating back and getting usually dimmer in the morning sector, and then retreating back poleward. This is the proton aurora looked at from the only global observations of the proton aurora that we ever had, which was the SI-12 instrument in the FUV package on NASA's image. And this is just an image of the proton aurora seen globally from Frey et al. In 2003. And this image is showing you, again, I would argue this image is showing you the inner central plasma sheet at all magnetic local times, with some caveats that I'll get to. This is done in the FUV, which is why they could, and with a imaging spectrograph that collected an image through the Lyman alpha part of the spectrum about once every 2 minutes. And so there are these grainy, because again, it's not a bright emission, these grainy, relatively structureless, even on the global scale, aurora. And SI-12 was fabulous, but I tend to look at things more from the ground. I will say that at the end of my talk, I'm going to give a plug for, I don't know what's going on to GDC, but proton auroral observations would be a very nice thing to have for that. And this is just showing you a stack plot of 7 8-hour Keograms from Gillam, Manitoba, showing the proton aurora on a relatively active day with a few substorms, on a day with a massive substorm, and then some quiet days, and then one where we have this one is what people used to call a pseudo breakup. I don't know if that term is still in common usage, but this is just what you see night after night after night. And usually, we had the Rankin Inlet, the Gillam, and the Pinawa photometers, but usually all of the proton auroral action was in the Gillam photometer, unless it was extraordinarily active, which would push the proton aurora down over Pinawa, or very, very quiet, in which case the proton aurora could be up over Rankin Inlet. But Gillam, Manitoba, by the way, is at 67 degrees geomagnetic latitude. And so usually the proton aurora got down to overhead 67 degrees geomagnetic latitude every night, and often didn't get much further equatorward than that. Now, this is just, we had in around 2000, I spent some time thinking about, brightness of proton aurora and some other things that were related to this statistical information about this phenomenon. And then what I've got here is from 270,000 MSP scans. Again, we got one a minute and this is from just the Gillum photometer. And there's a reason for that, which I'll get to, in a minute. But this is 270,000 scans. I took the peak brightness from each scan and just made a histogram. And just a rule of thumb for people who look at the night sky is that people will kick around the number 1 kilorayleigh. So that if something has a brightness of 1 kilorayleigh, then if it has some structure, you can probably detect it if you have pretty good vision. And so the vast majority of the proton auroral emission peak intensities in the Meridian scan are below 150 Rayleighs, which means that this is not a visible night sky phenomenon. You can see secondary electrons that are created in those charge exchange collisions. They cause a secondary aurora, which you can see in the green line, but that usually is about 15 times as bright as the proton aurora itself, and that means that usually you can't see it, right? It's usually down below a kilorayleigh, but if you have 100 Rayleigh proton aurora, then you can have a 1.5 kilorayleigh secondary aurora, and you can see that with the naked eye. But you're not looking at the proton aurora; you're looking at a secondary process. And this was also, by the way, when the Steve phenomenon kind of broke originally. This was why, when people said at the bar, near the University of Calgary campus, that they had taken a picture of the proton arc, which I thought they meant proton aurora by that. This is why I said, well, no, you didn't, because you can't see it, and you wouldn't be able to see it. Okay, so this is just kind of, again, by way of some statistical stuff, not my work by any means, but this is a Keogram of the proton aurora and a Keogram, simultaneous Keogram taken of the oxygen green line. And by looking at hundreds of such simultaneous observations of the electron and proton aurora, researchers in Scandinavia, in this case, but also in Canada, there's very similar, kind of built up this picture where you have the proton aurora here, kind of what it looks like on average, and so that's built up from a moving MSP, and then adding up and considering day after day after day, and then the electron aurora. And the idea is that the proton aurora is generally observed to be equatorward or at the equatorward edge of the electron aurora in the evening sector, and then it moves poleward of the diffuse pulsating aurora in the morning sector. And I'll refer to that at the end of this talk and what that means. This point here is an interesting point because this is the distribution of greater than 200 Rayleigh H beta observations from the ground. And I showed you the histogram showing the 150 Rayleigh and lower the bulk of the distribution. And there is a problem, because this is a very dim emission, there is a problem with calibration and cross-calibration between different ways that people have looked at this emission from the ground. And when people say it's a 100 Rayleigh proton aurora or a 50 Rayleigh proton aurora, you should always take that with a grain of salt, because we don't really, there are some discrepancies. The reason why I use the Gillum photometer data when I want to do quantitative work is that Dirk Lumertheim in Alaska and I we did a statistical study looking at the proton aurora from Gillum and from Poker Flat, which is at the same latitude. And when I say 20 Rayleighs with the Gillum photometer, Dirk Lumertheim's 20 Rayleighs with the Poker Flat photometer means the same thing. And so we called this like the Poker Flat Gillum Rayleigh, because we don't really know exactly how bright this stuff is. Okay, so where is this precipitation originating? So, again, I'm walking back out. That was a longer history than I wanted to go through, but anyway, I'm about halfway through the talk now. And so you have a satellite that flies along under the auroral oval, and a very good example, flying along here under the auroral oval, and a very good example of a satellite that had instruments that were good for looking at this was the NASA FAST satellite, and in particular the electrostatic analyzers, Chuck Carlson's electrostatic analyzers that would, that gave us beautiful electron auroral observations of the precipitating particles and the distribution function, but also gave us a lot of observations from the ion ESA instrument. And so this is sort of typical for what you would see, talking about the proton auroral region. And so this is, again, this is an ion electrostatic analyzer, but I'm just presuming that most of the signals coming from precipitating protons, or sorry, from protons as the satellite's passing through in the topside ionosphere. And so what you see here is this is a fast overflight of the Gillam Meridian scanning photometer. And I'm showing you here, this is the brightness from the H-beta channel on the Meridian scanning photometer for the scan that was closest to the time that FAST flew over. And then what you're looking at here is the integrated energy flux between 0 and 30 keV as a function of pitch angle from the ion channel. And then this is in the direction perpendicular to the magnetic field for a pitch angle of 90 or 270. This is the energy. This is the distribution as a function of energy, and again, this was with magnetic latitude here. And so if you look at this, the interesting thing for me is that, first of all, what you see very clearly is this empty upgoing loss cone all the way through from near the polar cap boundary all the way into what is the equatorward of the equatorward boundary of the auroral oval. And then what you see is this full downgoing loss cone, which I would say means that the downgoing loss cone is full of protons that are of magnetospheric origin. And this is what you see, it's often more structured in latitude, but this is what you see over and over and over and over again when you look. I've looked at thousands of these fast overflights of the auroral oval and looked at the ion data. And this is just, you always see this, double loss cone distribution equatorward of a region where the downgoing loss cone is just full all the way from what I will say is the equatorward boundary of the proton aurora all the way out to the polar cap. Now what's happening is that you typically see that band of bright proton aurora. In this case, this is just showing the integrated energy flux in the loss cone as a function of magnetic latitude. And you'll often see this kind of weird peak that's out here near the polar cap boundary, and then it's always increasing in brightness. And then you get this part in here where it's going to be, above about 5 or 10 Rayleighs, and therefore really, that's the bright part, what I call the bright proton aurora. So this is again, 2 Keograms from the Meridian scanning photometer at Gillam. And this shows you for 9 hours, the proton aurora, and I've just marked an, equator boundary and a polar boundary of the proton aurora. And then I plotted that over top of this electron aurora, the 5577 oxygen green line. And so what you see is this is the bright proton aurora that I spoke of. And then poleward of the bright proton aurora, you see all of these discrete features, and this is really around the polar cap boundary, the poleward boundary of the auroral oval, and this corresponds to the CPS all the way from the night side transition region all the way out to the open closed boundary. And then the proton aurora itself is coming from the inner part. It'll turn out it comes from the inner part of the central plasma sheet. And then in the morning sector, you often get this patchy pulsating aurora, and other diffuse aurorae, from within to equatorward of the proton aurora. And all of these map to different magnetospheric regions. But this is, even though there's the bright proton aurora here, the proton loss cone will be full all the way out to the open closed boundary. So this is a term, and I can't historically, I don't know who referred to this first, but Viktor Sergeyev and Kolya Siganenko and an American named Imhoff, who I'm not sure who he was, but There's a group of people back in the 70s and into the 80s that did a lot of work on the isotropy boundary. And the idea here is that we have a full downgoing loss cone and then what is an isotropic distribution outside of the upgoing loss cone. And then when we come across this equatorward boundary here, then all of a sudden we have an anisotropic distribution across the outside of the upgoing loss cone. And so we go from isotropic to anisotropic, and people call this the IB, or the isotropy boundary. And so what I'm doing here is imagining that I take 4 measurements with the FAST spacecraft as I transition across this isotropy boundary. And this is showing the, actually it's the ion integrated energy flux, not the differential energy flux, sorry. It's the integrated energy flux as a function of pitch angle. And the units don't really matter here, but what you see is poleward of the IB, or isotropy boundary, you see this isotropic distribution across the downgoing loss cone. And then as you move to lower and lower latitudes, usually within a ½ degree of latitude, you transition to a largely empty downgoing loss cone. And that's in the double loss cone distribution. As you move across that, this transition from isotropy to anisotropic distribution is a transition from bright proton aurora to equatorward of that, darkness in that spectral band. And so what's filling the loss cone? And so this is just a figure I made for a class I taught a while ago. And, I often like to point out that, if you just put particles in a static magnetic field and let them bounce back and forth between mirror points, if that's all that's going on, then the first time you do it, any particles that happen to be in the loss cone are lost to the atmosphere. And then after that, nothing's going on. There's no particles coming down. And it's a pretty boring magnetosphere in terms of what its effects on, on the upper atmosphere are. And so the fact that we see the sustained refilling of the loss cone on a time commensurate with the bounce time, which is what having this isotropic distribution really tells us, that means that these particles are somehow in strong pitch angle diffusion. Okay, and so we need to have some process which constantly is pushing these protons into the loss cone. Now, all aurora involves this kind of continuous refilling of the loss cone. When it happens because of a parallel electric field, we call that discrete aurora. When it happens because of some stochastic process, like wave-particle interactions that doesn't have much effect on the energy of the particle, from that process, we call that, for historical reasons, diffuse aurora. Dave Klempar, we have discrete aurora and the electron aurora. Dave Klempar told me once that he felt he had seen evidence of arcs, actual inverted V arcs in the precipitating protons seen in the FAST ESA instrument. And that's something I really desperately want to go back and revisit at some point in time, just for interest's sake. But the bright proton aurora that I'm talking about is understood to be a diffuse process. It's just pitch angle diffusion caused by some stochastic process further out in the magnetosphere. And so what's going on with that? This is the idea of here's one night of observations of proton aurora. This is just a Sigonenko model. And what I'm showing here is imagining there's a central plasma sheet and that there's something taking ions or protons from the central plasma sheet and kicking them constantly into the loss cone. And so it turns out that work that was done by Sigonenko in the late 70s and Sergeyev and Sigonenko in the early 80s, and then Buchner later in 92, depending on who you talk with. So there's the idea of this kappa parameter, and that is the radius, the kappa parameter squared is the radius of curvature of a field line locally, divided by the gyro radius of the particle. And so the idea is that when the radius of curvature gets smaller relative to the gyro radius, then you start to get non-adiabatic effects that violate the conservation of the first adiabatic invariant just because of that curvature interacting with the gyrating particle. And just a rule of thumb here, and this is something that, I think in the days of the computers that we have now. This is something that should be revisited from the point of view of understanding what's going on with this process. But generally speaking, if this radius of curvature to gyro radius ratio falls below about 8, or I call it kappa being less than 3, then you have enough violation of the conservation of the first adiabatic invariant to fill the loss cone every bounce period. And for that particle. Now this is obviously energy dependent because the gyro radius is energy dependent. But this curvature of the field lines causing this tight curvature of the field lines near the neutral sheet is understood to be the cause of most of the bright proton aurora. And I'm just showing this kappa parameter calculated in the Sigonenko 89 model with dashed lines and 87 model for Kp equals something and Kp equals something else. And then what you see here is that you can imagine we have the central plasma sheet, and then when the kappa parameter goes above 3, then the field lines are not curved enough to cause this loss cone filling. And so that transition to a double loss cone distribution is understood looking from the ground as we're staring at, for that energy of particle, we're staring at where it goes from strong pitch angle diffusion to no pitch angle diffusion, more or less, as a consequence of their gyro radii getting small relative to the curvature of the field lines. I'm just going to race through this. I just like to show this. It's some work I did back in the mid-2000s, but the idea was you can move electrons and protons, obviously, in a model magnetosphere, and this is just a Stern-Volin potential, and I'm moving equatorially mirroring particles, so we don't have to worry about the curvature drift, and according to E cross B drift, and also the gradient drift within the Sigonenko 87 magnetic field model. And and it's a Stern-Volin potential. And the idea is I can start particles further down in the magnetosphere and move them in and understand them as a source population for this proton aurora. And so what you see here, this is on the left-hand side is just, I forget how many, the few 100,000 particles that I moved in, and the color corresponds to their energy as they're moving in and gaining energy from conservation, the first adiabatic invariant. But this is just a distribution of, it's not very scientific. It's just I'm plotting the location of these particles just on many trajectories. And what you see are the ions, of course, being swept around on the dusk side, and that the ions having more energy when they're on the dusk side and in close to the Earth than when they were further out, and the opposite happening to the electrons, meaning they're swept around on the dawn side. And if you just naively assume, like forgetting about the fact that these are equatorial mirroring, and just naively assume this is the source population for the proton aurora and for the electron, for the diffuse electron aurora, then I can just take this and then map this down into an ionosphere, and what I get is a lot of proton aurora, this is not modeled, but a lot of proton aurora on the evening and dusk side, and diffuse electron aurora on the morning and dawn side of the magnetosphere. And I'll just say that this is a hard thing to do. Like these are very challenging observations, and so this data doesn't look great, but don't misunderstand. For me, I revere this data set. This is from Image Wick in orange, and from the SI12 in blue, and this is showing more or less what people see. But this is the only real shot that we ever had at doing this globally and simultaneously, and what you're seeing is the proton aurora and then the electron aurora over here, and there is this kind of crossover, and that's all I'm going to say about that. Okay, so now I'm talking about remote sensing the inner central plasma sheet. And so I want to point out that we have, like, so this is a Keogram from the Gillam MSP, and then this is a transit over the MSP by one of the DMSP satellites. And then for that, what I have here, this is the 5 Meridian scanning photometer traces of the proton auroral brightness as a function of magnetic latitude. And then I'm putting over this the downward integrated energy flux from the DMSP SJ7, I think is what the instrument was called, but anyway. And what you see is this something that is very repeatable, that if you just look at the integrated energy flux from DMSP or FAST, then that will give you a very good proxy for the proton auroral brightness. And I will be coming back to that. And then, so what I did was I found about 30, I believe, 32 overflights by DMSP of good meridian scanning photometer data from the Gillen photometer. And then Tom Soderellis gave me the B2I boundary, which corresponds to the IB, but that's in DMSP talk, and the B2I and from DMSP. And then what I did was compared this B2I, the distribution of B2Is, to a normalized Gaussian fit to each of the proton auroral that it transited over. And what I found was that, 29 B2I locations. And what I found was that the B2I or the IB, that I could get a good proxy for this by just taking, on average, the location of the peak and subtracting 1.4 standard deviations from the peak. And this turned out to be the best way I could fit everything to a simple parameter, all the B2Is to a simple parameter. And that's my proxy for the IB now, and my proxy for the B2I. But what this gives me, and then I'll just go to this next one here. And so I call this the optical B2I. And unlike single satellite passes, when you do this with SI12 data, you can get a global image of what the B2I is all the way around at all magnetic local times. And if I look at a time series from meridian scanning photometer, what I get is looking at the variation of this parameter. And I'll come back to what that means. Now, this plot here shows you the optical B2I from 200,000 meridian scans organized by KP. And it's actually kind of amazing, because this is one of the best things organized by KP that I've ever seen. And what that means is that I think, because of the relationship between KP and convection in the magnetosphere, that convection is intimately related somehow to the latitude of the proton aurora, and in particular, its equatorial boundary. And I'll just leave it at that. But one of the key things here that I wanted to get to was that if you look at this, this Keogram here, and this is my optical B2I that I'm tracing out here, and I look at GOES-8, and which is about 2 hours of magnetic local time east of Gillen. So it's in proton aurora, that's pretty close actually, because of the relative structurelessness of it. And what I'm showing you here is the inclination in solar magnetospheric coordinates of the GOES-8, the magnetic field at GOES-8. So it's a little bit above the neutral sheet at that point, or a little bit above the equator at that point. But what I've got here is this decrease in inclination, which corresponds to dipole stretching of the magnetic field at GOES-8, followed by a dipolarization, a significant dipolarization, and some just nothing much after that. And what I see in the optical B2I is its equatorward motion, followed by a retreat, and then staying more or less constant. And I noticed this very early on, that patterns that you see in the inclination at GOES-8 showed up in the optical B2I measured from the proton aurora. And so the inclination there's a very strong correlation between the inclination of the magnetic field at geosynchronous and the latitude of the B2I. And this difference in time, by the way, this is a massive substorm that happened out over towards GOES-8. And then this time difference of a half an hour is the time it took for that evolution of that dipolarization to be felt over the Churchill line on the west coast of Hudson Bay. And so what we did, we went out and we found about 16,000 or 17,000 times when we had 5-minute averages of 5-minute times where we had good GOES-8 magnetic field data and good simultaneous MSP data from Gillen, and just plotted the GOES-8 inclination as a function of the optical B2I at Gillen. And what you see is very, very strongly correlated, especially for 17,000 observations. And then Brian Jackal at the University of Calgary worked out a model of the inclination, where you could take the inclination of the magnetic field at geosynchronous and predict it based on UT, the optical B2I, and the dipole tilt. And this is a very simple model, but it turns out to be pretty robust. And to the point that we can get the magnetic field at GOES 8 to within the inclination within 5 degrees more than 95% of the time, just from a simultaneous observation of the proton aurora at Gillam, Manitoba. And this is just showing 4 traces of the modeled from the proton aurora inclination and the observed inclination in black at GOES 8. And if you just look at this night after night after night after night, it's more or less the same thing. This is the measured versus modeled inclination from that same study. And so what we're doing now is we're using the proton aurora, and we're staring straight into the geosynchronous, and I think I would argue, based on what I'm going to finish with, a little bit further out in the magnetosphere. And it's a very powerful way of remote sensing. Obviously GOES 8 gives us the information at GOES 8, but what we now have is the possibility of filling in gaps between geosynchronous satellites, for instance. And so, and then if we had, I'll argue for this is something we need to have. If we had the proton auroral imaging like we had at SI12, there's a lot of stuff we can do with this. And so you imagine this equatorial boundary of this proton aurora at all local times. Well, that is a measure of how stretched the magnetic field is in the inner central plasma sheet. And so you can watch this, for instance, this is going to be quick to go through, but this is time increasing as we go up, and this is going west and going east along the equatorial boundary of the proton aurora from SI12. And then what I want you to see here is when you go from when this is a measure of how far poleward or equatorward, red or purple, equatorward to poleward, red or purple, the auroral boundary has moved as a function of time. And then what you're seeing here is a westward traveling poleward motion of this B2I, which corresponds to, if you map that out to geosynchronous orbit, that corresponds to a westward traveling, I would argue, substorm current wedge at boundary, traveling at 25 kilometers per second as it goes along the equatorial part of the auroral oval. And again, I imagine that equatorial boundary, what we're doing is we're looking at these kappa equals 3 boundaries in the magnetosphere. And then when we watch that move poleward and equatorward, what we're watching is these boundaries move in and move out in the magnetosphere. And so it's a very direct observation. Matt Gilson, who did his PhD with Jimmy Rader at UNH, did a really interesting paper back in 2011. And it was looking at SI12, about 300 substorms with SI12. And what he found was that in half of those substorms, there was a splitting of the proton aurora that occurred, first a poleward motion in a local region and then a splitting of this. And this occurred as a consequence of turning off convection and turning on a dipolarization and substorm macro scale substorm current wedge in that azimuthally expanding region. And so this, again, we're looking at the proton auroral distribution, and we are looking at convection on one hand and dipolarization and stretching on the other hand. And so I just want to mention that there's an interesting observation I thought I made back in 2011, published in 2012, and it was that with 2 Themis spacecraft that were just separated in Z by about half an Earth radii, and so we could get the curvature of the field line, local field line, and then with the ESA on Themis and SST observation, we could take the curvature, and then we could calculate the energy where kappa equals 3. And then this is this critical energy that I've plotted over here. And what happens is that if that energy is below the bulk of the CPS ions, then they're all they're in strong pitch angle diffusion. And if it's above the bulk of the CPS ions, then protons, then they're not in strong pitch angle diffusion. And so this is a situation where the IB, I argue, in this 10 to 20 to 30 keV range has washed over the Themis spacecraft from being inside of the Themis spacecraft to being outside of the Themis spacecraft. And if we had proton auroral observations on the ground at the same time or from SI12, we would know exactly, as this thing crossed that 10 to 30 keV range, we would know exactly where that footprint was mapping in that meridian. during a very dynamic time. And that would be really very interesting. I haven't got really time to go through this, but Emma Spanswick did a paper that was published in 2018. And it's a nice, it's a quick read, it's a GRL, and I'd recommend taking a look at it if you're interested in this. And what Emma did was take the observations that we did on the ground with FAST and with DMSP and our proton auroral observations, and sorry, with FAST and their proton auroral observations, use the fact that the Themis ESA instruments were the same as the FAST ESA instrument and had the same form factor and everything, and then use that to infer from the ESA measurements what the proton aurora would be magnetically conjugate to the Themis spacecraft. And from that, and from doing some statistics, this is our distribution of proton auroral brightnesses, then what Emma did was actually demonstrate that the proton aurora almost never is magnetically conjugate to inside of 7 Earth radii, and the bright proton aurora peters out in latitude corresponding to the central plasma sheet ion population petering out as you go out past about 11 or 12 Earth radii. And so from about 7 to 12 Earth radii, it's not a big surprise, but this was a kind of like, yeah, now we know result. And so that takes me to the end of the talk. I'm just going to say a couple of closing remarks. These are made without, as I'm prone to do, just saying this stuff, okay? So pulsating aurora occur within or equatorward of the bright proton aurora. All arcs occur poleward of the peak in the bright proton aurora. The arc that brightens is on the poleward shoulder of the bright proton aurora. The bright proton aurora fades in the minutes before onset. Near midnight, the bright proton aurora originates from the 7 to 11 RE region, and proton aurora provides us with a means of remote sensing stretching. There's a couple of questions I've just put here. I haven't talked about precipitation, which is also very interesting, a source of one kind of proton aurora. And right now, I'll just finish by saying, I think it's a really valuable measurement. And I think right now we're kind of at the end of the road in terms of having good proton auroral observations that are readily available. And that's something I think our community should address. So thank you.
All right, great. Thanks for a wonderful talk, Eric. We have a handful of questions that we have some time to go over if you're not rushed to get out of here at 1.
I'm sorry I went a little bit long. So
no, not at all. So our first question comes from Jason Durr. It was at the beginning of the talk with regard to precipitation and the generation of the proton aurora. He asks, can one use the Doppler broadened spectrum to determine a height profile for the velocity dependence of the proton distribution function?
So I think there's not, I think that would be a very challenging measurement. You know, that like because you're looking through, you know, when you're looking up, right? You know, look like at magnetic zenith, you don't know where your photons are coming from in altitude, and when you're looking across, you're looking through a relatively thick proton auroral region. So this is typically going to be 100 to 200 kilometers or more in magnetic latitude. And so you can't look across and know where the photons are coming from. And so you're mixing signals from different places in the magnetosphere origin. And when you're looking up, you can't tell where this is coming from. And so I don't know, that's an interesting question. It's an interesting question, and I'll think about it. I'll think about it. Thank you.
Okay, great. So Natasha has one question. Are there science grade data of the proton aurora available? And is there any available during the Van Allen or MMS era?
Yeah, so there's, I can't say for sure that there isn't other than this, but there's always been a meridian imaging spectrograph at Poker Flat through the Van Allen and Themis eras, and to now, and it's still working. And that's operated by Don Hampton at the Poker Flat research rocket range or research range. We have had, Martin Connors has a proton auroral scanning photometer dedicated to Proton Aurora at the Athabasca University Geophysical Observatory, which has been running throughout the Van Allen probes. And Kazuo Shiokawa operates an imager with a Proton Auroral filter at Athabasca University Geophysical Observatory. And those are all science-grade observations. And then we in the Calgary group we've been kind of grinding the old Canopus MSPs finally into the ground. I mean, they've pretty much had it. But we have, but we have good MSP data up to at least into the RBSP era, certainly spanning much of Themis. And then in, I forget the year we put it out, but it's been out a couple of years now. We bought one Meridian imaging spectrograph from Don Hampton at Poker Flat, and a second one, which we put the one in at Lucky Lake, Saskatchewan. We're putting the second one in at Rabbit Lake, Saskatchewan, as soon as COVID-19 lets us travel. And all of that has data that's available. If you want to get data from our stuff at Calgary, you can contact myself or Brian Jackal or Megan Gillies. And if you email me, I can hook you up with somebody who will be probably more responsive than me in terms of dealing with that data request. But that's, I think, what we have out there. And so I think right now we're coming close to like 4 places where we measure Proton Aurora, all in North America. Great,
thanks. I'll also put some of your links on to the Calgary Data website onto our site after the talk. So Sergei Apatenkov has 2 questions. What is the energy range of protons that you observed with just the photometer? And is there a kind of one-to-one correspondence between the different energies in the spectrum? So he asks, are energetic protons seen if you get 1 50 keV proton? Is that similar to seeing 10 protons with 5 keV energy?
No, so you get very different things. So I said earlier, so I'll answer the second question first, okay? And so you look at the work of Davidson and some modeling work. I forget who did this, but Kazuo Shiokawa and Martin Connors had pointed out a while ago that if you have if you have a 1 keV or half a keV proton coming in, then you will have some of that Davidson broadening, but that will obviously have less collisions and less broadening because it's going slower, and also fewer collisions than if you have a 10 or a 20 or a 30 keV proton coming in. So you get this kind of increase in the broadening. But then as you start to go up above like 75 or 100 keV, then the protons are coming through, and they end up deep in a very much denser atmosphere. And so then they undergo all of these collisions, but in a very local region. And so actually you go from a broad to a broader to then a very much narrower precipitation pattern from a structure in the proton precipitation. And so when you're looking at the Proton Aurora from 150 keV, it's not like more of the Proton Aurora from a 10 keV proton, right? And that's one thing. The other thing is that when Emma did her study, she found that, like, she looked at fast. She looked at fast first, overflights of the Proton Aurora, and I forget how many, but it was more than 50 overflights. And what she found was that if you just took the part of the spectrum from the ESA instrument between 20 and 30 keV, and I can show you this. You take the part of the spectrum from between 20 and 30 keV energies, then you can, this is the peak Proton Aurora luminosity versus the peak downgoing ion energy flux. And it turns out that if you just take the peak energy flux, the energy flux between 20 and 30 keV in the downgoing loss cone, measured in ergs per square centimeter per second, and you multiply that by about 68, 65 to 70, then that's a very good proxy for the Proton Aurora brightness. And from that, she and I would conclude that that the Proton Aurora that we see, the bright Proton Aurora, is coming primarily in the 20 to 30 keV energy range of precipitation.
Great, thanks. So Paul Pickrell has a slightly simpler question. What altitude do you use for mapping the proton and the electron aurora?
So we of course, we have meant to explore, because we have overlapping fields of view from earlier Rankin Inlet, for instance, and Gillam photometer observations. And so we can see the proton aurora sometimes in both instruments, which are separated by about 500 kilometers and or 600 kilometers. And so that means that we could do some triangulation to get some simple things. But the proton aurora, our rule of thumb is 110 kilometers. And generally speaking, if you look at things like this is the solid curve is the solid curve here is the MSP, and the dash curve is like 69 times the integrated energy flux in the fast downward loss cone, and we're presuming 110 kilometers altitude, and these things line up very well, right? And so what that means is that 110 kilometers is almost always a pretty good guess for the height, okay, of the proton aurora. It's obviously got some depth to it, but I mean, you know, these are, I mean, you know, we're doing the best we can with that. Now, for the electron aurora, obviously things are all over the map, right? I mean, red line can be anywhere from 160, 150 kilometers, probably the lower limit of it, up to 300, 400 kilometers altitude. Green line, you know, we typically put in 110 kilometers as our estimate. But it can be down to 100 and up to 150, and actually, you know, and then the blue line tends to be down lower, and so we tend to put in 90 or 95 kilometers. I'm not sure when we do our automatic mappings. And then for the Themis white light data, we usually show things at 110 kilometers. And you can see with the Themis, it's really cool because when you look at the ASIs, with overlapping fields of view, if arcs line up, for instance, that means your height estimate is not wacky, right? But that's all, it's really rule of thumb kind of stuff, Paul.
Yeah, thanks. Our next question comes from Antonova, and is it possible to determine the proton pressure at the equatorial plane using proton aurora observations?
So I would think yes, actually. And it's something I've thought of. I'm a really observational guy, right? Like I've spent, you know, since I did my PhD and learned that I wasn't a good modeler, I've spent all of my time, you know, most of my time doing and having a lot of fun with these observations. And I think it's an obvious thing that one would be able to explore with simultaneous for example, Themis ESA observations and proton aurora observations are doing a statistical comparison like Emma did between properties of the proton aurora and properties where you could infer pressure near the equatorial plane. And I think it's something that's really worth looking at. I don't personally have the tools to do that. I mean, I probably could, but it's. So I think that's a really obvious question to ask. Sorry, that's terrible. It's not an obvious question to ask. It's a great question to ask. And if you wanted to explore it a bit, I'd be happy to help. Seriously.
Cool, great. So our next question comes from Suleiman, and it's in reference to your mapping and kappa slides. And so his question is, how do you foresee the configurations that you show changing if you were to include the dipole tilt axis or to change the dipole tilt axis?
Well, I mean, it doesn't really, I mean, like, you know, these were just meant to be, these are just kind of cartoons that I draw with a Sig-and-Enkel model. You know, and when so when Emma did her work, for instance, like she's she's looking at you know, like a range of dipole tilts. And, you know, you have to make some assumptions about where you are relative to the neutral sheet. But for a vast, I think for essentially all dipole tilts, the place on the magnetic field line on the night side where the curvature is the tightest is the neutral sheet, right? And so this process is going to be acting at the neutral sheet. It usually, I think, you know, the kappa boundary, kappa equals 3 boundary is going to be, you know, around the hinging distance, right? And so I think it doesn't really change the picture at all. It just makes it harder to discern in using data. And again, like when I did that thing with the Themis spacecraft, you know, it's you'll notice that Z here is minus 1.5 in GSM coordinates, right? And I'm presuming, you know, that we are right on the neutral sheet. Bacillus didn't yell at me when I made that presumption, so I think I was probably pretty near the neutral sheet.
Okay, great. So Natasha follows us up with a few slides after that with your ion and electron modeling. And she says, it seems from the model results that the trajectory of the ion and electron trajectories, that the proton aurora is formed as a result of ring current precipitation. Is this consistent with the location of the isotropy boundary?
No, I think these are largely not trapped particles, not drift trapped particles. So what you so for instance, in this modeling that I've done here, like all of these trajectories are open trajectories, all of them, and this is and again, I'm saying this with probably a little bit more authority than I have to say. I don't think this is ring current precipitation. I think this is central plasma sheet. You know, unless you consider the protons in the inner part of the central plasma sheet to be contributing to the ring current as they transiently pass through. There's a number of reasons for that. Well, I mean, like I'll just say I don't believe this is ring current precipitation, but I think, you know, the IB is going to be out. I mean, typically the IB is going to be out at 7 to 8 RE, which means the proton aurora is coming from outside of 7 to 8 RE, right? And so and then it, yeah. So I think that's correct. But again, it's a good question, obviously.
Okay, great. So we have one last question from Biswaji Oha, and it is, how is the proton aurora modulated by solar wind dynamic pressure? Or is it modulated by solar wind dynamic pressure?
So I will show you something. And that is, if I can dig this up. Just give me 1 second. I'm just digging up another figure. So this is a situation where we had solar wind dynamic pressure here. And then this is SIM-H measured at, you know, well, this is SIM-H. And so we had a pressure pulse with northward IMF. And that pressure pulse, when it arrive, here's that SIM-H again here, which corresponds to that arrival of that solar wind pressure pulse with northward IMF. And then what you're looking at here is a Keogram of the proton aurora. And what you see when that pressure pulse arrives, you see the proton aurora just step up in brightness, right? And that, I argue, is because you've compressed the magnetosphere and you've made the magnetic field larger everywhere. And that has made, by conservation of the first adiabatic invariant, the protons have more energy per proton. It turns out that from the fast pass before and the fast pass after, the B2I and the IB had not moved, not even a half a degree in latitude. It moves way equatorward following the southward turning of the IMF. But I would argue that you know, as you compress and buffet the magnetosphere with solar wind pressure, you see that. I've seen two events that were exactly like this. They're crystal clear. And I would argue that there's a very tight relationship between pressure and the brightness in the proton aurora, but it's convolved with other things. Like for instance here, where the IMF turns southward and the proton aurora gets brighter, that's not because of an increase in pressure. Because the proton aurora also empirically, it always gets brighter when it moves equatorward. And so this is just, I mean, I'm not entirely sure what's going on there, but this pressure pulse and this pressure pulse driving a step in brightness it's an absolutely clear relationship between what's going on in the solar wind and what's going on in the magnetosphere. And it's a mechanical, it's work. It's you know, the solar wind has done work on the magnetopause and that energy has gone into the protons. Cool, and the magnetic field and other things, of course.
Great. So we did get one last question from Xing Feng. And he asks, what was the altitude where the isotropic boundary is observed? And with a follow-up question, what is the difference between a double loss cone and a butterfly distribution?
So I can't answer the second question because I'd have to think about that and go and remind myself what a butterfly distribution is. But altitudes where we look at the B2I, I tried to find it in the IB rather. I tried to find it with polar data and couldn't see it with polar. But we see it very clearly on FAST at all altitudes that FAST was at. And so I don't know what the peak altitude of that was, but we see it all the way down to like 800 kilometers on DMSP. And I forget, it's been a while since I've looked at FAST, but I forget what perigee was for FAST, but all the way from perigee to apogee, you know, all of those altitudes, we could see we clearly see the transition in the loss cone.
All right, great. So that brings us to the end today. That's all the questions. Thank you for a wonderful talk, Eric. That was really informative. Next week, we'll be continuing with the aurora and the night side, and Liz McDonald will be talking about the Steve phenomena. Thanks again, Eric, and we hope to see everyone next week.
Well, thank you, everybody.